Hi guys, Miss Raymond here again, and the last video you saw was naming ionic compounds without a transition metal, and now this time we're going to name ionic compounds that have a transition metal. So they don't start with the alkali metals, alkaline earth metals, or aluminum, but they start with a transition metal instead. So the first ones that we're going to name are going to be binary ionic compounds, and remember that bi means two, so it's basically just going to have two different atoms. It's going to have two things together to make that ionic compound. So here, for this rules, we're going to name the metal ion or the cation, also known as the cation, first. Then we're going to leave a space for the Roman numerals, so we're going to go ahead and use parentheses for that. We're going to name the anion, and if it's a regular anion, if it's binary, we're going to change that ending to IDE. If it's polyatomic, we'll worry about that later. Then we're going to figure out the charge on the transition metal, and I'll be showing you how to do that today. Once we know the charge on the transition metal, the charge of the transition metal is going to go inside those parentheses, and it's going to go in there as a Roman numeral. So let's get started. So here's our very first one. Our very first one is called iron chloride. Now notice that I left space for that Roman numeral. Any transition metal is going to have to use this Roman numeral, and you'll notice why, because if you look at this example here, we have FeCl2, but over here I have FeCl3. So there's a big difference between them. If I call them both iron chloride, it's really hard for me to explain to someone, hey, go get me the iron chloride. Well, which iron chloride? Because there's a huge difference between these two compounds. So we're going to have to indicate that by using a Roman numeral in the name, and that Roman numeral in the name is going to tell us the charge on the iron. Now remember that we know the charge of the alkali metals. We know the charge of the alkaline earth metals. We know the charge of aluminum. Those, we know how many they want to lose to be like the noble gases. But the transition metals, we don't know exactly how many they want to lose. And so we have to go off of their compound or off of their name to figure that out. So let's just look at FeCl2. So here I have FeCl2. Now, the way that we're going to do this, we're basically going to break this down. We have to remember that the positives on the left have to equal the negatives on the right. So what we're going to do, I'm going to make some notes here in blue. We look at chlorine on the periodic table. Go ahead and look at chlorine on the periodic table. Pause this if you don't have it out. Now, if we look at chlorine on the periodic table, we know that chlorine would like to gain one electron, so it would like to be a -1 charge. If we take that -1, and if there's two -1s, then the total negative charge is -2. Now, for all compounds to be neutral, they have to have an equal number of negatives for the number of positives. So if this is -2, then the positives have to be +2. Notice how many irons we have here. There's only one iron. So what is that charge on that iron in order for this to be +2? If you said 2, you're correct. Now, the Roman numeral 2, we're going to go ahead and write a Roman numeral 2 right here. Now again, that's indicating the charge on the iron is +2. That's where we're getting the Roman numeral 2. Our next one, again, looks like iron chloride, except we know that it's different. So again, we have FeCl3, and we're going to go ahead and we're going to look at this and we're going to say, okay, FeCl3, this time I'm going to use red or pink. And in this one, again, chlorine's -1, so our negative charge total is -3. Well, we know that our opposite has to be +3. Since we only have one iron, what is that charge? Oh, if you said 3, you are correct. So the iron has to be +3 here. Since there's only one iron, it has to be +3 in order for it to total to +3 charge. Okay, our next one is copper with a blank sulfide. So we're naming this just like we were naming our binary ionic compounds in your last video, but now again we're putting in that Roman numeral. So the Roman numeral here. So we have CuS. Now I'm going to go ahead and use my blue to indicate my notes. Sulfur, I look up on my periodic table, is a -2. Since there's only one sulfur here, that total minus charge is -2 total. The positive has to be equal but opposite. Since there's only one copper, think about what that charge would be. If you said +2, you're correct. Notice here, we have another copper sulfide, but the Roman numeral is going to be different because we can see that CuS and Cu2S look very different. So again, I've got Cu2S. I'm going to make my notes here in red. Sulfur on the periodic table is -2. There's one of them, so that makes a total of -2. My positive has to be equal but opposite. Since there are two sulfurs, what do you think the charge, or excuse me, two coppers, what do you think the charge on the copper is going to be? If you said 1, you are correct. So since the charge on the copper is 1, I'm going to put the Roman numeral 1 right there. Our last one here is cobalt phosphide. Now remember, it sounds funny to say phosphoride, so we say phosphide. Now as far as the charge goes, if we go ahead and write COP, and we're going to write our charge of what we know phosphorus is -3, and there's one phosphorus, so that total is -3. Our positive has to be equal but opposite. So to make that equal but opposite, since I have one cobalt, what is the charge on that one cobalt? If you said +3, you are correct. Good job. So keep in mind, if we have a transition element, we're going to go ahead and name the transition element. We're going to go ahead and name the anion. We're going to change that ending to IDE if this is binary. But then we have to leave space for that Roman numeral, and that Roman numeral we can only figure out by breaking it down by charge. For these next 5, I want you to go ahead and try these on your own. Make sure that you have your periodic table out with you so that you can see what the name of the elements are and so that you can see the charge on the anion. Go ahead and pause it and try them now. Did you pause it? Are you checking your answers? I sure hope so. So here we have our answers. We have nickel 3 bromide, because if we go ahead and look at NiBr3, whoops, that's a 3. The nickel, to figure that out, we know bromine is -1, so that adds up to -3. This has to be equal but opposite. There's one nickel, so what's the charge? That charge is 3. Hopefully you figured out the rest all the same. And hopefully you also remembered that nitride is nitride, not nitrogide, because it sounds funny. Oxide is oxide, not oxygide. The other thing I want to point out is I do want to point out this last one here because a lot of people mess this up. Let's go ahead and look at this last one. If I have MnO2, I'll make my notes in blue. So oxygen is a -2 charge. That totals up to be -4. Manganese would like to be +4. If there's one manganese, what is the charge on that manganese if it totals up to be 4? That total is 4. Good job. Now these are basically the same, except we're using some polyatomic ions. So using your knowledge from our last video and using your knowledge from this video, I want you to go ahead and pause this and know that these are some transition metals, and some of these have polyatomic ions, so go ahead and name these accordingly. How did you do? Did you get them right? Hopefully you got these right. Hopefully you looked at your polyatomic ion chart that was on the back of your periodic table or that's in the back of your book in the upper right corner, and you're able to name these. One thing I want to point out, zinc never changes charge, but because it's a transition metal, we usually do go ahead and use that too, even though it's always going to be 2. Same with silver. Silver is not multivalent, as you read about, meaning that it has more than one charge, but we're going to go ahead and use that 1. The other thing I want to point out is gallium looks like it's not a transition metal because it looks like it's on the right side of the periodic table, but because it's below the staircase and it's not touching the staircase, it acts like a transition metal. So we're going to treat it like a transition metal, and we're going to go ahead and we're going to use that charge. Now, if you're having trouble with any of these, please, I urge you to write these down, try them on your own again, and if you're having trouble, please come and see me. Thank you.